Greetings, Physics 2001, Section 102 students. This is lecture 25, which will actually be the final lecture. So normally when I do final exam review, I do a review session on Tuesday where I say a little bit about just a reminder of the content we covered over the course of the semester. And then on Thursday, what I do is I go over any problems that you're interested in us solving. I don't really think there's a great way to satisfactorily reproduce this kind of experience. So what I've done instead is I've expanded this lecture a bit where I'm going to do the Tuesday type of lecture sort of where I go over, just a reminder of the general content, how you can recognize certain types of problems. But then I will intermix sort of a Thursday-like experience by mentioning, hey, these are the kinds of problems, that you need to be able to solve. Before I do that, just some organizational things. You do have a homework assignment due on Friday, and you do have your final lab due on Friday as well. Regrettably, the exam, has to be the original final exam. It has to stick close to the original final exam schedule, so we have to have some open exam times on Monday, the following Monday, 2:30 to 4:30 p.m. There's nothing we can do to avoid that. However, what we're going to do with this exam is like we did with exams 2 and 3, is where you're going to have some amount of time to take the exam. So in this case, you're going to have 2 hours to take the exam. Once you start, you only have 2 hours to do it, but you can have that 2 hours anytime within a given time window that we're going to announce. So the time window is likely going to be from Monday morning to Tuesday evening, but I can guarantee you that it will encompass this 2:30 to 4:30 time. And an email announcement is going to go out, soon on when the actual exam time will be. I'm recording this the weekend before this lecture, so we haven't quite decided yet. So please do watch your email. Okay, so general studying tips. I'm going to go over these, but this is basically the one 3-bullet summary. Is look at your old in-class questions. Those are good exam questions. Those, and of course the homeworks, but the top hats are like it's a smaller list for you to go through. You really always need to try a problem before you look at the solution. It doesn't really help you if you just look at the solution. It may seem like you're learning, it may seem like it makes sense and you're understanding it, but you're probably not. It's just kind of a fact of the matter. You really should focus on the solution processes, and that's part of the purpose of this lecture, is to remind you what processes are. The equations, you need to have the original equations on your equation sheet, but the processes and knowing what the relevant equations are, that's really the most important thing. As far as studying goes, please don't put it off to the last minute. I know there's a lot going on in your lives, and so it can be tempting to just study, the Sunday before and go for it. That will probably not turn out very well. So please try to start studying now. Use the week before the exam to study to the extent that you can. Okay, so this is just a overview of everything that we have covered. So just to remind you that it basically breaks into these different topics where you have kinematics, forces, torque, energy work, momentum conservation, circular and rotational motion, springs and simple harmonic motion, fluids, thermal physics, and thermodynamics. There's, of course, many lecture notes that you can peruse for these. And if you want supplemental information, these are the relevant chapters in the OpenStax textbook. The final exam, is about roughly half, I would say, maybe a little less than half on this last third of the course. And then a little around half or so is on the first 2/3 of the course, I'd say is a roughly fair representation of what the final exam looks like. What I'm going to do is I'm going to go over just reminders. So for instance, for each topic, for kinematics, a 1-slide reminder of that content, and then a 1-slide set of example questions that are kind of what you might want to study. Keep in mind that anything we've covered in the lecture is fair game. Any of the homework problems, practice exams, top hat questions, pre-class assignments, even really the lab reviews any of that is stuff that we expect you to be able to do. Now, most of it's redundant, so it's not like it's all that much extra. But in general, anything that we've covered so far is technically fair game. It's just to say, don't just study this particular set of slides and say, okay, now I have it all mastered. You do need to review some of the material you've gone over. Just some general studying tips. This is more my personal view, but I think it works pretty well in general. What you should do for studying is review the notes first. Just read through them, right? Spend an hour or two reading through the notes. Not everything in deep detail, but just kind of refresh your memory. Then go ahead and start trying some practice problems. So for each of those topics I listed on the previous page, try a couple practice problems per topic. So for instance, go to Top Hat. The questions are all open for review. Go to Top Hat and just try a sampling of questions from a given lecture, maybe 2 or 3. And genuinely try to answer that question, and then go ahead and look at the lecture notes for the solution. Once you've actually tried the problem, look at the lecture notes. And then I would just say, you really should kind of just iterate this, right? Iterate this process until you feel that you're pretty comfortable with most topics. Then I think what it's time to do is I don't have it written here, but what I think it's time to do here is you probably should create a first draft of an equation sheet. Would be useful. Then use that equation sheet and take the practice exam in a realistic setting. So sit down and take the practice exam in a 2-hour window and try to do it straight just using your equation sheet. So at this point, how much have you studied? You've probably done, let's say, 2 hours reviewing the notes, probably, I don't know, 3-4 hours working through practice problems, doing this iterative process, and you have another 2 hours here. So far we are, 6 to 8 hours in. You've done most of the studying to where you probably can do a good job, but at this point, you may want to really zero in on what you're still struggling on. Okay, going a little bit extra if you want to really ace the exam. Then when it's all said and done, create your final equation sheet. So take the equation sheet that you had for your practice exam and hone it a little bit. Because in all likelihood, when you take the practice exam, you might realize like, oh shoot, I wish I had this one equation. I needed that, or I needed this piece of information. So try to do that. General comments, like I said, something like 8 hours is probably needed to do well. If you really want to do well, maybe you need to do more, but I realize that, like, let's get real, you have lives. So I think 8 is a realistic amount you can shoot for, and you'll do quite a good job. Making the equation sheet, right, should supplement your studying, but don't think that it's substituting it. That's not a really great way to comprehend the material. Physics is learned by doing. So as far as tips for taking the exam go, really the best thing you can do is get some good rest before, get set up in a nice quiet environment to the extent that you can, and just try to stay calm while you're taking it. So, for instance, if you come to a question that seems extremely unfamiliar, you don't really know where to go with it, just make a note on a piece of paper. Okay, I skipped question 10, and then go to the next question, and do that as needed to build up your confidence. Because more often than not, you'll find that when you go back to the question that you skipped, once you've kind of got some mojo going, you've solved some problems, you find that, oh, okay, this does look a little bit familiar, and you can maybe take a better crack at it. So just really try to stay calm. When you're done with the exam, assuming you have time, and you should have time given the 2-hour window, there's probably going to be time for you to go back and look through and read the question carefully again and make sure that you read it and that you didn't make a mistake interpreting the question. Read it carefully, make sure that you solved the problem that was being asked. And at the end, you can also go through each question in lon kappa and make sure that you do have something submitted. For each question, it'll have a visual confirmation that you submitted it. So do make sure that you do that. If your internet just totally dies during the exam, send me a message as soon as you can. Once you get internet back, or maybe using data on your phone or something like that, send me a message, and we can figure something out. So in Kappa, I can see how long you've already been in the exam and what you've been doing. It's kind of creepy, actually. It tracks your activity pretty heavily in Kappa. And so I can figure out, how much extra time do you need. So note, now I'm going to do kind of a whirlwind tour of the class. Note that these are just kind of tips for a given topic, and it's hitting the highlights. This is not going to be completely comprehensive. So anything presented in the class is fair game so far. So along this semester. So this is like my disclaimer statement that the rest of the slides are intended to help you, but they're not necessarily a substitute for going back and reviewing the previous material that we've covered over the course of the semester. So the first topic that we've covered in the semester after the basic algebra and introductory stuff was kinematics. So how do you recognize a kinematics problem where you're going to have a trajectory, right? Usually you'll have a trajectory, something describing a trajectory, motion with linear acceleration, something being dropped, for instance. Those are kinematics questions. How do you solve these? I think the best way to go about it is to draw it, figure out what do I know, what do I want to know, which equations will get you from, from what you know to what you want to know, and then just work through the algebra. This is true for actually all of physics. If you can draw it, do draw it. What do you know? What do you want to know? And then of your list of equations, what gets you there? So in kinematics, you have this list of basically 6 equations. That's most of what you need to know. And what can be tricky sometimes with, what you gain experience with over practice is which equation do you want to start out with? What gets you what you want to know from what you already know? So sometimes you might accidentally pick the wrong equation and wind up in a dead end, but just if it doesn't work out, just go back and try another equation and see if you can solve the problem from there. And note that there's often more than one way. You can often use any one of these equations or combinations of them to get your solution. There's usually more than one way to do these type of problems. Keep in mind that if you have 2D kinematics, you're basically actually breaking this up into 2 1D kinematics problems. So for instance, if you have projectile motion, then really you have constant motion in the horizontal direction and free fall in the vertical direction, just as an example. What are some examples of typical types of problems you might have with kinematics? We might, for instance, have an object and we might drop it and then ask you questions about that object. So for instance, how fast is it going right before it hits the ground? How long does it take to hit the ground? So let's say you get a problem like this, what do you need to do? Well, keep in mind these context clues. So if we say something's dropped, then that means that the initial velocity is 0. The vertical acceleration, as long as you're on the Earth, and if it's not specified, that's where you are, is always little g, which is 9.8 meters per second squared. And in this particular example, we know the height. So let's say we want to know how fast is it going. You could use energy conservation to do this. But if you're going to use kinematics, then here, what do we want to know? In this example, we want to know the final speed. So that's what we want to know. We know initial velocity, we know acceleration. If you stare at your equations long enough, you'll see that this equation is the one that'll get you there. So this y minus y naught, that is the height between where it was dropped and the ground. For the acceleration, you use little g. You know the initial velocity, and you can go ahead and solve that. If we want to know how long does it take to hit the ground, well, then you need to pick an equation with time in there, and one where you know most of the rest of the information. So if we know the difference between the initial and final heights, we know that it's dropped, so we know the initial vertical velocity, so that term cancels, and then we know little g is the vertical acceleration, then you can solve for time. Another type of question you might be asked is you might have an object that you're basically given the information about at some point in a trajectory. So you might be given the information and say like, okay, it starts with some speed at some angle, then you need to determine the velocity at some other point in time. So in this case, what do you know? You know the magnitude of the initial velocity, and you know the angle. so you can work out the horizontal and the vertical components. You know that projectile motion, the vertical acceleration is little g, and there is no horizontal acceleration in projectile motion. So we use SOHCAHTOA, to get our velocity components. This is just our trigonometric relationships for the triangle. And keep in mind, no horizontal acceleration. And for the vertical acceleration, little g is your acceleration. But also keep in mind that the vertical velocity is 0 at maximum height, and the velocity is also symmetric about the trajectory. So if you know the velocity at one height in the trajectory, the magnitude of the vertical component of velocity is going to be the same when you're back at that same height in the trajectory. And then you can also always use this equation to figure out the velocity at any point in time along your trajectory. Going on to topic 2, forces and also equilibrium. So how do you recognize these problems? I mean, usually we tell you that there's a force. Okay, there's some pushing or pulling, there's some friction involved. Usually the word force is often used, or perhaps there will be a free body diagram that is being drawn. What distinguishes this from a torque problem is that there's not really a rotation axis. And I would also note that it's not mutually exclusive, right? You can use force and torque in the same type of problem, and we've seen that throughout the semester. So for force problems, what are the tips? You often should draw a free body diagram. If you're going to have a lot of forces involved in a situation, even more than one, draw the free body diagram. Apply Newton's first law, so the sum of the forces is equal to the mass times acceleration. Note that you have to break this into components. This is really the sum of the horizontal components of force is equal to the mass times the horizontal acceleration. And it's really the sum of the vertical component of the force is equal to the vertical acceleration. And then all you do is you just do the algebra to figure out your missing force or your missing acceleration. So these problems are always boil down to F equals ma. Note that if your object is not accelerating, that means A is 0. That means your sum of your forces is 0. The forces must be balanced. So what are examples of typical problems? So let's say an object has some initial speed and a constant force is applied to it for some amount of time, and we want to know what the final speed is. Well, what do? So you know the initial velocity in this case, you know the force that's applied, you know the time interval over which it's applied. You always use F equals ma for these problems. And then you keep in mind in this case that the acceleration is the change in velocity over time. So you would be able to figure out that final speed based on these two equations. Let's take another type of problem, a tension problem. So let's say you have two objects connected by a rope, and let's say that the rope goes through a pulley. Let's say these two objects are blocks. We know their masses, and we know the acceleration of one block. Okay, this is just an example problem. You might want to know, okay, what's the acceleration of the second block, and what's the tension in the rope connecting the two blocks? So in this example, we know the masses of the two blocks, and we know the acceleration of one of the blocks. And what we want to note here is that they're connected. If you're connected by a taut rope, so like a rope with tension in it, or by a firm object, then they're going to accelerate together. So in this case, if we know the acceleration of one block, we actually know the acceleration of the other, that they are the same. As far as the tension in the rope, you want to use F equals ma, where you're talking about the components of the force. And here you just need to be careful defining the system. What is the definition of the system? And you'll see examples, there's lots of examples when you go back to the forces lectures where we get a lot of practice identifying what the system is. Moving on, sort of expanding forces to the idea of rotation, we have torque and static equilibrium. So how do we recognize these problems? Well, either there'll be a torque mentioned, or you'll have a force and an angular velocity mentioned, or we'll have a picture or words noting that there's a force acting on an object, but not directly to the center. So you might, for instance, have some pivot point, or maybe the center of a wheel, and then a force applied at some distance from the center of a wheel, or the pivot point. And then you'll know that there's a torque problem that's involved. And right, the torque is equal to the perpendicular component of the force times the distance from the axis of rotation, as is shown here. So what are some tips for solving this? If your object is not rotating or accelerating, then you want to use static equilibrium. So that means that the sum of the horizontal forces is 0, sum of the vertical forces is 0, sum of the torques is 0. Or you might, for instance, be asked for an angular acceleration or a change in angular velocity over time. This is the other torque equation that you need to know. It's basically F equals ma, but for rotation. So tau is equal to I alpha. The torque is equal to the moment of inertia times the angular acceleration, so the change in the angular speed. So for these, often you're going to want to draw a free body diagram. If you have more than one force involved, that's a good thing to do. If the axis of rotation is not given, you may need to pick the axis of rotation. The way that you do this is if there's a force involved that you want to ignore. So for instance, you know it's there, but you don't know it yet, you haven't solved for it. You can put the axis of rotation where that force is applied, because then the distance from your axis of rotation to that force will be 0, so that force will apply 0 torque. And then you just do the algebra for the static equilibrium equations. So these torque problems are more or less always the same. It's solving one or more of these equations. Typically, you're at least solving the torque equation, and you may or may not have to bring in the force equations, depending on what information is applied. One thing to note is that if you have an object with an extended mass, so for instance, a person, or let's say a post, if the weight or if the mass is evenly distributed along that object, then the geometric center of that object is the center of gravity. That's where the weight is effectively coming down. So for instance, we have this person, and let's say they're pivoting about their feet, then like they're doing a push-up, then the center of gravity in the person, we have it labeled, and that is the force exerting a torque. If this person's mass were completely uniformly distributed, then the center of gravity would be their geometric center, and that force would be pulling straight down, for instance. So what are some typical problems you encounter for torque and static equilibrium? So let's just take the first example. Let's say you have multiple forces that are applied, some distance from the axis of rotation, and we want to know what the net torque is. So in this case, you know all the forces and you know the distance from the axis of rotation. So this always comes down to just summing the torques is equal to the sum of the different perpendicular components of the force times the distance of the axis of rotation. And these i's, this just indicates the ith force, right? So you might have any number that you need to combine. If you're a counterclockwise torque, that's positive. Clockwise is negative. What is a given or a similar type of problem that you might also encounter is you might be told that it's not rotating, so you're in static equilibrium. You might be given several forces and several distance of axis from the axis of rotation, but you might be missing one distance from the axis of rotation or one force. And then what you do is you say, okay, in static equilibrium, the sum of the torques is equal to 0, and then you can solve that algebraic equation. Another type of problem that you might have is you might say, okay, you have a net torque. Maybe you've had to solve for it from these forces, or you're given that net torque, and you have an object that's rotating at some initial speed. And the question is, how long does it take to go from rotating at some initial speed to some final speed? So let's assume that you know the net torque, or you have solved for it given the above situation. You know the initial angular speed and the final angular speed, and all you need to solve for is the time. How long did it take to do this? Well, remember, just like F equals ma, we have this equation for torque that tau is equal to I alpha. So the torque is equal to the moment of inertia times the angular acceleration. And recall that the angular acceleration is the change in angular speed over some elapsed time. So moving on to energy and work type problems, how do you recognize these ones? Typically, you're given the height of an object at some location, and you're asked for the speed at another location, or you know that there's some non-conservative force that's specified, like friction, and you're asked for an energy change, or you can imagine various variations on that theme. So the tips for solving these is, this energy conservation equation. This is one of the main ones. There's basically two that you really need to know. You need to know this energy conservation equation, and then the equation for work from a force over some distance. So the energy conservation equation just says your initial potential energy, recall that that's mgh, mass times little g times height, plus your initial kinetic energy, recall that that's 1/2 mv squared, 1/2 times the mass times the velocity squared. That's equal to the final potential energy plus the final kinetic energy plus any work done by non-conserving forces. So if, for instance, energy is injected via work, like from an engine, then this is positive. If we're removing energy, for instance, from friction, then this is going to wind up being negative. So for instance, if you have something like friction, like a force over a distance, then the work that's being done by that non-conserving force is the force times the distance traveled times the cosine of theta. So this is the angle between the force and the distance traveled. If the force opposes the distance traveled, so if they're 180 degrees apart, this cosine becomes -1. So that's why if you have some work that's removing energy from the system, this winds up becoming negative, right? Because you'll have minus W here. Then all you need to do is work through the algebra. So some notes here, potential energy, keep in mind this is always with respect to some reference height. You may have to choose this, or you may be told, hey, this given height is height 0. So the typical non-conserving forces that you need, if friction is one that we deal with, sometimes we may deal with air resistance. If there's an object that's being dented in or indented as it's impacted, that's a good example of a non-conserving force. If you're asked information about a trajectory, but you don't need the time information, you may go with this option instead. So the example from kinematics where I said, let's say you have an object at some height and you drop it, what's the speed before it hits the ground? You could instead just go ahead and use energy conservation. And that problem is actually a little bit quicker to solve that way. So what are some typical energy and work example problems that you might see is, for instance, you might have an object start out with some initial velocity, an initial height, and you might want to know the velocity at a later height. So in this case, you know the initial and final heights, you know the initial velocity. You pretty much always wind up using this equation, the conservation of energy equation. Here, there's no non-conservative force, so our W is missing, right? We don't need it. Keep in mind that the kinetic energy is 1/2 mv squared, so sorry, that should be v squared. And your potential energy is mgh, where the h is the height, it's always relative to some reference height. Then you just work through the algebra. Another typical type of problem you might have is, let's just say, for instance, you have an object, it's moving at some speed, you don't know what it is, you just know it's moving at some speed on a horizontal surface, and it hits a patch of sandpaper and comes to rest. And you know the mass of the object, the coefficient of friction for the sandpaper, and how far it traveled along the sandpaper. And you want to solve for the initial speed, for instance. So in this case, you know those things that I just said. Because it's at rest, you actually also know the final velocity is 0, and there's no height change, so you can ignore potential energy. So again, we're going to use that general equation of conservation of energy, but here we can ignore potential energy because it doesn't change. So the initial kinetic sum of kinetic energies is equal to the sum of final kinetic energies. In this case, that's 0 because our object ends up at rest, and that's then equal to the work done by non-conserving forces. Here, you basically have a force along some distance. You have the friction force being applied along the distance that you're traveling. And so that is what we need to do for the work in this equation. That work is going to be equal to the initial kinetic energy, and you can then solve for the velocity using the 1/2 mv squared. For the friction itself, keep in mind that the friction force, if it's moving, you use kinetic friction. So the kinetic coefficient of friction times the normal force. If it's static, remember that the static friction force is less than or equal to the static coefficient of friction times the normal force. And remember that for a horizontal surface, the normal force is just the mass times little g. If you have a tilted surface, then you're going to have to use trigonometry to figure out how much of this mg is oriented perpendicular to your surface. And we did many examples like that in the past. For instance, a block sliding down a ramp is a good way to figure out how to calculate the normal force for a given geometry. So then the next class of problems that we have deals with momentum and momentum conservation. So how do you recognize these? Objects are colliding, basically, then momentum is involved. So it might be worth drawing the initial and final situations, or at least doing, if you don't do this, do some kind of accounting, where you say, okay, in this column, I'm going to put all the initial stuff, and in the next column, I'm going to put all the final stuff. You want to make sure you know who's involved in initial and who's involved in the final. Why that's important is, for instance, let's say you have two objects initially moving, and then they collide and stick together. In your initial situation, you have two separate masses and velocities to contend with. In your final situation, you might only have one combined mass and combined velocity to deal with. So be careful just doing this accounting. Then you just need to employ momentum conservation, right? So the sum of the initial momenta is equal to the sum of the final momenta. This is a vector, so we're really saying the sum of the horizontal components of momentum in the initial situation is equal to the sum of the vertical components of momentum in your final situation. And then you're just working through algebra to find that missing information. Another thing that might be useful is if you're asked to identify if a collision is elastic, inelastic, or completely inelastic, then you can use this type of flowchart. So, if you're told that it's stuck together, boom, it's completely inelastic. If they're not stuck together, then you need to calculate, is any kinetic energy lost? So you can calculate the kinetic energy for the initial situation and the final. If none is lost, then you're talking about an elastic collision. If some kinetic energy is lost, then you're talking about a inelastic collision. Here's two typical types of problems. Let's say, for instance, you're told about two objects that initially have some mass, they have some initial velocity, they collide, and this results in a final velocity. So, and then you're asked, let's say, what type of collision is it? So you know the masses, the initial and final velocities. If the problem says they stuck together, then we're all done. Then it's completely inelastic. If it doesn't say that, then we have to use momentum conservation to figure out what are the final velocities of the objects involved, or if you're missing a final velocity. Then you can calculate the initial and final kinetic energy, go back to your flow chart and say, is this was kinetic energy lost? If so, it's inelastic. If none was, it is elastic. Another type of problem that you might be asked is you're told that an average force is applied to an object over some time, and you want to know what's the change in momentum. Maybe you're given the mass and you want to know what the change in velocity is. Same problem, basically. So in this case, we know the force and the time. Recall that the impulse, J, is defined as the average force times the elapsed time over which that force is applied to an object. This impulse is also equal to the change in momentum, so the final momentum minus the initial momentum. And so then you can go ahead and use this to figure out what the change in momentum is. If you're given the initial velocity, you can figure out what the final velocity is, and things along those lines. So the next thing is circular and rotational motion. In the class, we covered them separately, but they're really kind of an extension of the same thing. So I'm going to treat them together here. So how do you recognize this type of problem? It might be told it's rotating, or something's moving, but it's not in a straight line, right? It's going in a circle, or it's rotating, right? Then you're talking about circular or rotational motion. So there's kind of a patchwork of equations you need to do here. It depends. If you're given information about rotational motion, but you need to convert to linear motion, then you need to do that. So for instance, we'll go over an example in a moment where you can figure out how far linearly you've traveled using this definition of the angle as it relates to the arc length. If you want to know how fast linearly you're traveling, then you need to use this relationship for the transverse or tangential velocity and how that relates to the rotation of the wheel. If something is spinning, a different sort of set of scenarios, if something's spinning but changing its mass distribution, then you need to employ angular momentum conservation. So the initial moment of inertia times the initial angular speed is equal to the final moment of inertia times the final angular speed. And then finally, or not finally, almost finally, another type of thing you might have is you say a force is applied at some radius. What's the change in angular speed? You need to use this analogy to Newton's first law. This torque is equal to moment of inertia times angular acceleration. Tau is I alpha. One thing to keep in mind is the centripetal force, what is keeping an object moving in a circle. So for instance, what is keeping this tire rotating in a circle like this? That is the centripetal acceleration, and that is equal to the radius of your object times the angular velocity squared. So then the centripetal force is ma, because F equals ma, so it's mass times those things. And just as a reminder, there's basically a nice analogy between linear quantities and rotational quantities, and that might help you remember these equations and how you use them. So what are some examples of typical problems? Let's say that you have a wheel and you know the radius of the wheel, you know the angular speed of the wheel, and let's say it rolls for some amount of time. And then the question is, okay, well, how far has this thing rolled, like linearly? How fast was that wheel moving? What is the magnitude of the force holding an object to the radius of the wheel or to the rim of the wheel? Those are some example questions we could ask. So in this case, we know the radius of the wheel, we know the angular speed, we know the elapsed time, and we're going to have to be told what the mass is of this object that's stuck to the rim of the wheel. So in terms of how far is linearly traveled, we'll keep in mind that you can get the linear distance as the arc length. And the arc length comes from the definition of an angle. So an angle is equal to the arc length divided by the radius of that circular motion. If you want to know what the linear speed is, you can recall that there's this angular velocity is the change in angle over change in time. And this transverse velocity is equal to the radius of the wheel times that angular speed. And then to address the final question here, if you have an object being held to the rim of the wheel and you want to know what that force must be keeping it there, then it's always the case that F equals ma, and in this case the centripetal acceleration is the one you want. So the mass of the object times the radius from the axis of rotation times the angular speed squared, which, given this relationship above, is equal to mv squared over r. So the mass of the object times this transverse velocity squared divided by the distance from the axis of rotation, or the radius r. So for another different type of problem in this class of problems, let's say we have an object rotating at some rate with some mass distribution, and suddenly the mass distribution changes, and we want to know what's the new angular speed. So in this case, we're told the mass of the objects in the distribution, their distances from the axis of rotation, their angular speed initially, and we just have to keep in mind angular momentum is conserved. L is I omega, so the total angular momentum is constant. And therefore, the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. And for some typical moments of inertia, that you should have written down on your equation sheet and know, if you have a point mass, or basically an object moving some distance from the axis of rotation, like we actually have in this problem, then it's equal to the mass of the object times that radius squared. Let's say you have a solid object like a disk. The moment of inertia for a disk is 1/2 times the mass of the disk times the radius squared. Okay, moving on to the next topic is springs and simple harmonic motion. So how do we recognize these? Well, if a spring's involved, then it's a spring. If a pendulum is involved, then it's going to be simple harmonic motion. If something's repeating, right, going in circles or moving back and forth, that's when you want to use simple harmonic motion. So as usual, it's, what do you know? What do you want to know? And then look at your bank of equations here that are all written here. And how do you get from what you know to what you want to know? How do you do that? And these equations, you should just have written down. So your spring force is equal to the spring coefficient, this K, the stiffness coefficient, times the displacement from the basically resting length of the spring, and the angular frequency at which this mass plus spring system oscillates is equal to the square root of the spring constant divided by the mass of the weight. This is the angular frequency. Be careful, it's not the regular frequency. You need to relate the angular frequency to the regular frequency this way, and the frequency to the period in that way there. If instead, let's say you have a pendulum swinging, the angular frequency for the pendulum is equal to the square root of little g divided by the length of the pendulum. General notes, right? A cycle is anything repeating, oscillating, doing circles. Some examples of typical problems. You might be told, for instance, an object oscillates with some frequency, and you're asked, okay, what's the spring constant? Or maybe you're asked, what's the pendulum length? So in this case, you know the oscillation frequency. You need to be careful. Remember, the oscillation frequency is not the angular frequency. These are different, right? This omega is equal to 2 pi f. 2 times pi times f is equal to omega. So you need to be careful because you know the equation for the angular frequency and how that relates to the spring constant and the mass. And you know how the angular frequency relates to little g and the length of the pendulum. So you're going to need to do some conversion between the regular frequency and the angular frequency. Or similarly, if you're given the period, you're going to need to convert to that angular frequency to use these equations. Another type of problem you might be asked about is, let's say you have a graphical visualization of an oscillation. So let's say you're shown for instance, the position or velocity or acceleration versus time. And then you're going to be asked about one of the properties that's not on the graph. So if position's plotted, you might be asked about velocity and acceleration at given points in the motion. If velocity is given, then you might be asked about what the position or the acceleration must be, and so on. So here, what are the things that you know? You know from your spring force that F is equal to Kx is equal to ma. You know that the force is going to have to be maximum at the amplitude, because that's when x is biggest. You have the largest displacement at the amplitude. That's the definition of an amplitude. You know from this definition as well that the force needs to be a minimum at zero displacement. It's zero at zero displacement. And if you think about your oscillations, if the force is a maximum at the amplitude and the minimum at zero displacement, then the acceleration is going to be the same, right? Because F equals ma. Your velocity kind of does the opposite, right? It's going to have to be a maximum at zero displacement, and it's going to be a minimum at the amplitude. Okay, so how about fluids? Another topic that we covered near the end of the semester. How do you recognize this? Basically, you have something floating or something flowing. In this case, in this semester, because of the pandemic, we cut out covering floating stuff, which is a little bit too bad, but it is what it is. So here you're basically going to have an object sitting stationary in a lake, for instance, or you might have a flowing fluid through a pipe. So if it's stationary, then you're only going to have to use the pressure is equal to rho gh. If it's flowing, you basically have two equations you need to keep in mind. You have the continuity equation. The density of a fluid times the area of that fluid times the velocity of the fluid is going to be constant. So if, for instance, the pipe gets smaller and the density stays the same, the velocity's got to go up. Now what you can also use is Bernoulli's equation. And if you want to figure out what the change in pressure is as you flow through the pipe, because for instance, let's say the diameter changes, or you want to figure out what the change in pressure is because the height of the pipe changes, like from one section to another, then you need to use Bernoulli's equation. And it's really just a statement of conservation of energy. So you have the initial pressure plus the initial potential energy, rho GH, plus the initial kinetic energy, 1/2 rho V squared, is going to be equal to the sum of the final bits of those guys. So you just need to be able to use these two equations. So remember that continuity says, just even qualitatively, if you squeeze a flowing fluid into a smaller diameter pipe, it's going to have to speed up. What does the Bernoulli equation say, in essence? If you slow down a fluid, the pressure is going to have to increase. Okay. Also keep in mind the pressure in a fluid is going to have to be height dependent. It's relative to a reference height. We often define it relative to sea level, where you're going to have atmospheric pressure, which is about 1.01 times 10 to the 5 Pascal. Remember that just definitions, if you're talking about pressure above atmospheric pressure, that's the gauge pressure. If you're going to include the atmospheric pressure in the whole thing, that's the absolute pressure. What are some typical fluid problems examples? Let's say we have a fluid flowing at some velocity that's specified in a section of pipe that has some radius. And then later on, let's say something's going to change. So for instance, maybe your pipe height changes, maybe your radius changes, or maybe both change, and you want to know what's the change in pressure. So what do you know? You're given the initial radius. Keep in mind that if this is a pipe, it's a cylinder, so the area is going to be pi r squared. Okay, you need to know that. The initial velocity is given, and then you have some new properties. So there's a new relative height or a new radius, so therefore a new area, something like that. So if you want to change in velocity, you're going to use Bernoulli's equation again. Oftentimes we will tell you that the density doesn't change, and so then you can just cancel the density out. So then you're just comparing the product of the initial area of the pipe times the initial velocity, comparing that to the final. It doesn't need to be equal. For changes in pressure, you're going to need to use Bernoulli's equation. Keep in mind that if you don't know the final velocity, you may have to use the continuity equation to get you there, to get you that final velocity. And then you can go ahead and use Bernoulli's equation. Or another type of problem is, let's say an object is located some depth below sea level. And we'll specify the pressure at sea level is 1.01 times 10 to the 5 Pascal. And we would specify what the density of the fluid is. Let's just say it's water, which is 1,000 kilograms per meter cubed. Sorry, that should be a cubed there. So the question then is, what is the pressure at a specified depth? Well, here we know the pressure at sea level, and we know the density of water. We know our depth below sea level, so we just use pressure is equal to rho GH. Right? Straightforward enough. If two objects are at the same height in a given fluid, they must be experiencing the same pressure around them. So moving to thermal physics, how do we recognize these problems? Well, we're going to have an object that's being heated or cooled, and it's responding to that in some way. Or a temperature we're being told is changed, and we want to know the change in pressure, for instance. So the first thing you need to do is make sure your temperature is in favorable units. You're going to need it in Celsius, you're going to need it in Kelvin. Fahrenheit are not useful units, so you may have to do a conversion. If heat's being transferred, you have this heat transfer equation. So the heat change for a given object, the heat flow, is equal to the mass of an object times the specific heat, or the heat capacity, times the change in temperature. If you have a hot object touching a cold object, keep in mind that the hot object is going to lose some heat, and the amount of heat it loses is going to be equal to the amount of heat that the cold object gains, as long as we're talking about a thermally isolated system. If you have a phase transition, you need to keep in mind that there's some heat required due to the phase transition, and that's equal to the mass of the object doing the phase transition times the latent heat. And if you're going from a liquid to a gas, that's vaporization latent heat that you're talking about. If you're going from a solid and a liquid, then that is the latent heat of fusion that we're talking about. You may also be asked, is an object expanding? And in this case, you might be asked, how does the length change? Some notes here, stick to Kelvin or Celsius, make sure your units are consistent, and just keep in mind that right? An object with a higher heat capacity, what that means is it takes more heat input to raise the temperature. So even qualitatively, you know about this. What are some examples of some thermal physics problems? So let's say we have an object and it has some length. It's initially at some temperature. It's heated to another temperature. Let's say that we're given the linear expansion coefficient and we just want to know what's the new length of the object. So your initial length is given in this example, your linear expansion coefficient is given, and your initial and final temperatures are given. So what you need is this linear expansion equation that the final length of an object is equal to the, this is just true. The final length of an object is equal to its initial length plus the change in length. You have your linear expansion equation that their change in length, so delta L over L, is equal to the linear expansion coefficient times the change in temperature. Be careful that if you're asked for what the new length is, you need to plug this delta L into this equation here. And again, be careful, what temperatures you're using. You're often going to be given that coefficient in favorable units, Celsius or Kelvin. If you only know the initial and final temperature in Fahrenheit, you need to convert to take that into account. What's another example that you might have is, let's say we have an object with some heat capacity and some temperature. Let's say, for example's sake, we add that to a cup of water, and that water starts out with some temperature and has some heat capacity. And what we want to know is what's the final average temperature once these things have cooled to equilibrium. So we know the initial temperature of the object, we know the initial temperature of the water, and we know their heat capacities. Sorry, that should say TW. I don't use it later, so I guess it doesn't matter. What you need to know for this type of equation, right, is the heat lost by the hot object is equal to the heat gained by the cool object. For each of these Q's, right, this is MC delta T. What matters here is that if you have an initially hotter object, then the change in temperature for the hotter object is going to be the initial temperature minus your average final temperature. For the initially cooler object, delta T is going to be the average temperature that you wind up at minus the initial temperature for that cooler object. So you plug these into your delta T and you plug these equations for the heat lost and the heat gained, and that's how you solve these problems. If a phase change were involved, you need to use this Q equals ml. If you're considering following the temperature of an object versus the heat added on a graph, keep in mind that you're going to have in the parts of the graph where the object is changing temperature, you're going to have a line, right, because this is a linear equation. In the parts of the graph where you're at the temperature that you have a phase change, then here this is temperature independent, right? So you're going to have a flat line on that part of the phase diagram, on the part of the temperature versus heat graph. You're basically going to keep adding heat but not change temperature. So that happens at the phase changes. So moving on to the last topic that we covered in the class is thermodynamics. How do you recognize these problems? We have a gas undergoing some change. In this case, we're always going to do ideal gases in this class. Or we have a heat engine or heat pump or a refrigerator that's being discussed. Or maybe we're directly shown a pressure volume diagram. So things to keep in mind, PV is equal to nRT. Pressure of the gas times the volume of the gas is equal to the number of moles times the ideal gas constant times the temperature. So if your temperature changes, you can figure out how the pressure has changed, for instance. If you have something like a heat engine or a refrigerator or a pump, this operates in a cycle. And keep in mind that means that there's no net internal energy change. Delta U is equal to 0. For some cases, you also are going to have maybe a cycle or maybe just a few of these pressure volume changes. Then you need to use this equation, the first law of thermodynamics. The change in internal energy is equal to the heat added to the system minus the work done by the system. Keep in mind that work being done by the system would be, for instance, if the gas is expanding and pushing a piston out. Work being done on the system, which you'd put a negative number here, you'd have a minus W, that's like, for instance, compressing the gas. You may be able to use the type of transition that might offer you a shortcut, and go back and look at the last lecture. or 2 lectures ago rather, and you will see a cheat sheet summary for your different transition types, how some of this information has changed. If you have any, heat engine, heat pump, refrigerator, this is always true, right? The amount of work that's put in or generated, it's going to depend on the difference between the heat transfer to or from your hot reservoir and cold reservoir. Okay, and so for instance, the heat flow between the engine or the refrigerator or the pump, between that and the hot reservoir is going to be Q sub H. The heat flow from to or from the cold reservoir and our engine or pump or refrigerator, that's Q sub C, and that is equal to the work done by the system. You may need to know the efficiency of your object. So, that's just how much do you get out over how much stuff do you get in. And you have your different efficiencies listed here. And they're different equations because, for instance, for an engine, what you want out is work. What you put in is heat from the hot reservoir to the cold. For a pump, there's a coefficient of performance, a heat pump. What you want out of that from the heat pump is Q sub H. You want heat. What you put in is work. For a refrigerator, your coefficient of performance is how much heat are you pulling from the cold object. You're creating an unnatural flow of heat. That's what you want your refrigerator to do. That goes to the refrigerator, the object itself. So that divided by the work you put in, that's going to be the performance for that object. Keep in mind that the Carnot efficiency is going to be the maximum theoretically possible efficiency, and you tend to calculate that by substituting temperatures in for heat flows, as we covered in the previous lecture. Keep in mind that the direction that you move on a PV diagram matters. So for instance, we have pressure versus volume here. If we start at state A and go to state B, then the area under the curve, that is the work being done by the system going from A to B as it expands. If instead you go from B to A, you're going left or right to left, that's negative work. So that's work being done actually on the system, or negative work being done by the system. So then you'd integrate this and then it'd be negative. What are some examples of typical problems for thermodynamics? For instance, we might add heat to a system with a fixed pressure and cause the volume to increase. And we might ask you, okay, what's the change in internal energy? So in this case, we know the change in volume and we know the amount of heat added. We're pretty much always, for these thermodynamics questions, going to start out with this law of thermodynamics, that the change in internal energy of the system is equal to the heat added to the system minus the work done by the system. This is always true. If your pressure is fixed, then you can go ahead and use this equation that the work done by the system is equal to the pressure times the change in volume. And after you add and subtract heat, that's also going to change the temperature, and you could use PV equals nRT to figure out how much that temperature changes, for instance. And then a final type of example problem that we can talk about is, let's say you have a heat engine or a refrigerator or a pump, and you're told there's some amount of heat flow to or from your hot and cold reservoirs, to or from your engine, and some work that's being put in or extracted. And then you're asked to find the missing piece of information. So how much work did you get out, for instance? You do that with energy conservation. Or you might be asked what the efficiency is. And again, those efficiencies are just defined over here. Keep in mind that your heat engines, right, these operate in heat engines and pumps and refrigerators. These all operate in a cycle. Your change in internal energy is 0. So for all these examples, the heat added over the course of the cycle is equal to the work done by the system over the total cycle. Your high temperature reservoir is going to add heat for the cycle. Your low temperature reservoir is going to remove heat for a typical heat engine, right? So therefore, the heat for your cycle is going to be Q sub H minus Q sub C. Really, you need to pay attention is heat being added to or from. Because for instance, in a refrigerator, you are actually adding heat from the cold reservoir and dumping that into the refrigerator. And then you are forcing the refrigerator to send heat from itself to the nominally much hotter reservoir. Keep in mind always in these cases, what goes in must come out. So these heat flows all need to sum up in some way. And of course, the efficiencies are there. So this basically concludes the class. Again, this would normally be 2 lectures, so my apologies for just berating you without any practice questions. What I want you to do now is to use the time for the Thursday class to work through practice problems and try to use these notes to guide you as to what type of practice problems would be useful. So thanks for working hard this semester. I think people did put in a pretty good effort overall, and I think it was quite good. My sincere apologies that this had to be finished online. I tried to do my best here to do something that was flexible for you because I'm sure your schedule has changed. I know mine has, but something that would kind of approximate what you'd get out of our in-person meetings. I hope that we achieve something quasi close to that. So, best of luck on your final exam. Just, take your time to put some studying in, do it over the course of a handful of days, and then you'll be fine. It'll work out. This semester, keep in mind that if you get a passing grade, you can opt for the satisfactory if you want to do that. For some context, typically the average grade in this class is a C+. So if you get a B or better, you did pretty well, just so you know. And then if you have any questions about physics in this class or astrophysics that cross your mind, feel free to email me. I usually try to answer people. I have a few people from the past that still email me occasionally with somewhat random physics questions, and I'm totally cool with that. That's what I get paid to do. So that concludes this lecture and concludes this semester. Best of luck in all of your future endeavors.